given rise the pressing issue on electronic waste and generating posing the significant environmental and health challenges. However, it can give rise to pressing issue for environmental and health challenges like batteries as emerge as a paramount concern with the vast array of e-waste contributors. For example, alkaline battery. People typically electronic waste throw in the environment and it disposed in alongside with other households such as food and plastic waste. So it has been very hazardous. Like there are some components like MN, Zn, chlorine, like flammable poison organic electrolytes are harmful to the humans when they enter in the body. However, it is a very important topic to recycle or reactivate these materials for any other benefits. So, according to our goal, here we can use reactivated cathode material for triboelectric NAND generator. Like these are the hazardous issues of electronic waste, like soil pollution, air pollution, and water. And these are some health issues according to the metalines like lead are hazardous for central nervous system, mercury are for kidney damage, cadmium for stomach and lung disease. These are some specific examples of the health issues because of e-waste. So in this work we have tried to reactivate the that cathode material from electronic alkaline battery waste. There are three main ways of the recycling. First one is pyrometallurgically, second one is hydrometallurgically, and third one is direct recycling. However, according to the hydrometallurgically and direct recycling, pyrometallurgically is very simple and cost effective. And it is also less expensive apart from these two. So here in this work we have choose the pyrometallurgical approach to reactivate the cathode material from waste alkaline battery. In the first step, we have dismantle and separate the grinding and sieving the cathode material from waste alkaline battery. Then we have reactivate using a fill furnace in several temperatures starting from 100 to 800 degrees Celsius. And according to the pyrolysis temperature, the surface morphology and the triboelectric device performance are also increased. Here the experimental section like fabrication and mechanism of triboelectric NAND generator based on reactivated cathode material. Here we have the PET as a substrate material to cover the device, and our synthesized reactivated cathode material used as a tribopositive layer, and the PTAP was used as a tribonegative layer. And in figure B, like it is the actual triboelectric mechanism like fully pressed, releasing after fully separated and pressing. With this cycle, the triboelectric NAND generator will perform. Like the result and discussion. In the result and discussion, here we show the efficient analysis of all reactivated cathode materials synthesized at different temperature from 0 degree to 800 degrees Celsius. If we see the image, it can be found that according to the pyrolysis temperature, the surface morphology of the reactivated cathode material was altered. Like for 0 degree, for 0 to 200 degrees Celsius, it's like aggregated nanoparticles was observed, and from 400 and 500 degrees Celsius, the porous morphology was found. Because this temperature was sufficient to make exact tribopositive material for the triboelectric NAND generator, and after that temperature can be found that the material was transferred into the crystalline nature, and the oxygen, the carbon and oxygen content was also altered according to temperature. Here is the EDS and its corresponding images from figure A2 to H2 and A3 to H3 and A4 to H4. Here we can see the XRD of the all reactivated cathode materials. It is also we can also found the similar results according to the surface according to the pyrolysis temperature. The material crystalline phases are altered from 0 degree to 400 degrees Celsius. It can be observed that the crystalline nature, and at 405 degrees Celsius, the porous crystalline phase was observed. And after that, the material start to decompose, and it convert into the another material. The color formation of the formation also indicates the change in the material's properties. And in FTR spectra, similar results was observed. The surface functional groups of the reactivated cathode materials was altered. Electrical measurements after fabrication device, we have take some electrical measurements. Like initially in this figure, we have take different tribo positive and tribo negative layer. In first figure, we have choose our synthesized material as a tribo positive layer, and the material shows high triboelectric performance. Later, we have changed our tribo positivity layer with the recycled anode material of waste alkaline batteries, and it show lower performance as compared to the reactivated cathode materials. Later on, we also alter the tribon positive to tribon negative layer. We have altered reactivated cathode and reactivated anode material as a tribo negative layer. In this case, we also found less performance as compared to the reactivated cathode material as a tribo positive layer. Overall, in this experiment, we found that reactivated cathode material are good tribo positive material apart from the tribo negative and triboactive anode materials. Later on, we check we have made 7 devices based on the temperature like 0 degree to 800 degrees Celsius, and from figure A in figure A and B, we can found that the 500 Celsius is the exact or sufficient temperature to reactivate the proper tribopositive material for tribolytic nanogenerator. Here we can show according to the temperature, the performance will increase, and after laterward, the performance will decrease because the material was start to decompose. It converted into the another material. In the next set of electrical measurement, we have altered the tribo negative layers from cellulose, nignin, PET, and PTFE. But here we can found PTFE as a highly tribonegative layer, and we can found higher performance in this device. In the next set of electrical measurements, we check it's like without reactivated cathode material and with reactivated cathode material. And we can found that the without reactivated cathode material, there is no any performance in nanogenerator. And after incorporation of reactivated cathode material as a tribo positive layer, we can got high performance. In this experiment, we also check the effect of applied frequency. Like as we know that the triboelectric nanogenerator is the principle based on contact triboelectrification. Like between this is the contact electrification between tribo positive and tribo negative layers. So we have based on the applied frequency, the device was show their performance. So we have start to apply external frequency from 2 hertz to 5 hertz, and at higher applied frequency, we got higher output performance in terms of voltage and current. Figure C, D show its corresponding results. Later on, one more parameter like device size is also influence in triboelectric nanogenerator performance. So we have checked from small device to large scale devices like 1 by 1 to 4 by 4, and at 4 by 4 we can get the maximum performance. So it is also confirmed that the device size is also one more important parameter in triboelectric nanogenerator. In the next set of electrical measurements, we have checked its polarity like tribo positive, tribe positive and tribe negative. And also we check the capaciting charging performance using three different capacitors like 0.1 microfarad, 4, 4 microfarad and 10 microfarad. This indicates it's also show good capacity storing performance. So it can be implantable in other micro source electronic gadgets. So our device show good performance. In the next electrical measurement, we check its power density, and we got maximum power like for 502 meters per square centimeters per square. It is also which also check its cyclic stability near about 4,000 cycles, 40,000 cycles. It show stable performance. So we can confirm that also our device is also uh, in highly stable, so we can use in electronic gadgets. Like in the next step, we check its applicability in real world applications like glowing LEDs and charging uh, operating calculators. Here we use as our time device as an energy source, and here in figure 4 and 5 we can check its glow LED. Near about 200 LED was glowing using our time devices, and the capacitor and the calculator was also operate good as shown in figure B. Overall, the conclusions are our work is focused on the development of waste-based materials for high potential triboelectric energy harvesters. These materials was also synthesized from simple and efficient pyrolysis process. Notably, this experiment was conducted at low temperature without the need for activating gases like nitrogen, hydrogen, and argon. So these techniques confirm the reactivation of cathode material and reveal the significant changes in surface morphology, functional groups, and active oxygen-based varying reactivation temperatures. Based on the different reactivation temperature, the corresponding surface morphology was studied, and its corresponding correlative output performance was also studied. The device, the temperature 500 degrees Celsius was demonstrated remarkable output voltage and current and power density. This superior performance can be attributed to relative rough surface and high availability of oxygen content, which enhance the triboelectric effect in device. To evaluate the stability of the developed material, it shows the 4,000 consecutive cycles, and the results demonstrate good stability of this duration. Overall, this finding not only contribute to the recycling of waste alkaline batteries, but also provide a promising pathway for the development of efficient and environment-friendly materials for future triboelectric energy harvesting. And this work was published in Nano Energy Impact Factor 17.6. Thank you. Thank you for your patience.